Okay, let's get started. Today we are going to look at solid-state electronics, which is a final year course. I'm going to be presented by Zungeru of the Center of International Studies, MIT. Now, today we are going to be looking at Lecture 3, which is the career transport. And last week we talked about state career transport, but today we are going to continue with career transport. Last week we concentrated on career. Today we are going to look at career diffusion. Last week we looked at this career drift. But before I start, we are going to look at two different things under this career transport. That is, using the fixed law for career diffusion and the diffusion current. Generally, in this course, this career diffusion under this course, the main purpose of teaching this topic is for you to have a detailed understanding of career diffusion and to be able to apply fixed law for diffusion current and to be able to calculate diffusion current from career concentration gradients. At the end of this course, you will be able to explain the physics behind career diffusion and also explain and apply fixed law to career flux density. And also, you'll be able to explain and apply this career flux density to diffusion current. Now, what is even diffusion? Okay. Now we look at a simple example. You have sample of water with you there, right? And here we have ink here. So we look at what diffusion is all about before we could see how it also applied to electrical engineering. Okay. Now, I will help you so that I don't want you to get yourself messed up. Okay? So, please let's observe what is happening as we put some drop of this thing. Please be observing what is happening. It's supposed to be a little small, since because of too much anyway. Small. Okay. Please, let's be observing. One, because I just put it too much, but we could be observing what is happening in one of it there. As you can see, we have particle of water and some particle of this ink. And you can see what is happening there. At the top, when we put the ink, at the top, the ink was highly concentrated, right? As time goes on, it tries to go down to the side that is of less concentration, right? So that means, if you look at this graph here, here we have two things in the silicon diode that we're going to use for this course, okay? These two things are the electrons and the holes, that is the particle. Like you have water and this ink, right? Now, if we look at electrons, assuming in the silicon diode, okay? Now, the electron and hole are the two particles that are inside that medium. Now, what happens if electrons start to move from one place to the other? Okay, they want to displace holes at one end, right? As they move in a random way, like as you can see from that graph, they will try to go down to the side that is of lower concentration, right? And because of that movement, there is velocity because of the distance moved with time. So, and also the mobility of the electron, and that will cause flux. And that is what we'll be looking at today. Now, according to someone who has studied these behaviors, which is fixed, he applies first law to say that what will happen for those two particles, that is the electron and hole, which will cause this what we call diffusion flux, is proportionally to the negative of the concentration gradient. And as we said, the concentration gradient is what? The concentration of either the hole or the electron with distance, as you can see from the other graph, okay, that it moves with distance. So as it keeps on moving, the concentration what? Reduces. So it tries to displace the hole. So why the hole will also move to the electron? Because of that, they try to balance the content of the silicon. And that is what will create the current. Now, for electron, according to the physics, it said that the flux, that the diffusion flux is equal to minus d of n of x over dx. That is d of n of x. That is the concentration, the change in concentration of what the electron with respect to the distance, and that of the holes is change of the concentration of the holes with distance. While d is a constant of what? Proportionality, and that is what we call the diffusion coefficient. And that diffusion coefficient is, it depends on the mobility of either the electron or the hole, and also the velocity at which those particles actually move. So now, let's look at what that diffusion creates. That is the diffusion current density, and which is equal to the charge by what we've seen the other side, which is the carrier flux. And looking at it, for holes try to move in the direction of the flux, while the electron move opposite direction. That is why you have minus q. Q is the charge, and for each of them you have minus for electron and plus for holes. Now, if we let's lay example on one of this using the equation 4 that is in your notes there. Okay, we're able to solve this simple example. Equation 4 there, because we are looking at holes. Now the question says the whole density in an n-type silicon wafer is that, and decreases from 10 raised to the power of 14 to 10 raised to the power of 13. Okay, between x is equals to 0 and x is equals to 1 micrometer. As you can see from that gradient, it moved from 0 to a distance s. Okay, now this is what we have. Then we are asked to calculate the whole diffusion current density, given that electron charge is this and the whole diffusion coefficient is that. If you apply that equation 4, you're able to what? Get the diffusion current density.
That's
okay?
time.
Thank you so much. So if you cannot do it now, you're able to do it at your home. So that, but what I was trying to tell you is that at the end of it, you're able to get what diffusion current density is all about. So at the end, what we actually learned today, in summary, we've learned that a diffusion current is produced by what? Concentration gradient, and which depends on either the hole or the electron. And carriers will move faster in response to the gradient in order to balance the particles in the medium. Thank you so much for attending today's lecture. If you have any questions, my email is there. You could email your query to me. Thank you.
Thank you. Comments? Sure.
I like that you listed the learning outcomes at the beginning, because it really outlined what we were supposed to learn from the session. I think that it was a bit rushed, but I think that I wouldn't have been able to do the exercise because too much was being thrown at me at one time that I wouldn't have been able to process it all. But I think that if there was more time, then we probably would have been able to go through it in more detail.
Other observations?
Yeah, I found it thoughtful that you brought the printed outline because you were presenting us with so much information. It was useful for us to be able to look back at what we had just gone over. But like Jerry, I did find it a little hard to keep up. So maybe it would have been nice to just focus on one of the learning objectives instead of all three of them that are printed here.
Anything else?
One thing I find interesting is the little demo we had. Is that one was able to explain to us what diffusion is all about, the concept of diffusion. This is taking it from biology and then to electronics. So I was able to at least keep track of that. Okay, if in biology, diffusion normally takes place from the area of high concentration to low concentration, same also is happening in the silicon chip. So I enjoyed that part.
That's a good point about finding hooks for people where giving them places to jump in. Imran, did you have any?
Yeah, just only thing because the diffusion you showed a lot of equations for that one. Because sorry, I was start from the beginning. But because everyone has a problem with the time, so if you can cut off some of the theoretical explanation, because I think because it's a 5 minute class, you don't need to really go to the theory of because it's just an introduction. It's all about how you actually design the class for 25 minutes. So it could have saved a few times, but I really like the experiment, you know, like it gave us a interest to join the class and see exactly what happens.
Thank you so much.
Right. Yeah, no, I think it was, I think the learning outcomes were great. And I also think it's good, you'll notice that Adam said, oh, remember last time we talked about whatever. So it's really good to remind students what you did the previous time, because I think I mentioned this before, they're coming from other places, they're coming from another class, they're coming from breakfast, they're just waking up. And so if you just say, okay, I just want everybody to remember what we did last time, let's just all get on the same page, that's a really good thing to do. And I thought the learning outcomes were great. I think they probably were a little ambitious for 5-7 minutes though, so keep that in mind. The other thing I think you want to keep in mind is the demo is really interesting, it's really good, but you might want to force us to like pull something from it ourselves, you know, the idea of not just telling us what's happening, but saying, okay, somebody tell me what you notice, or here's some questions I want you to think about while I do this. Again, it kind of makes it more of a learning, personal learning thing rather than just something we're watching. So keep that in mind, I think. And then for many of us, you know, we do something, maybe we don't try it out, and so we don't realize how much ink is going to come out or something. And then just on to follow up on what Jonathan said, the idea so that it's really great, you can say, okay, I can understand higher concentration to lower concentration, but then there's a little bit of a curveball in there because they have charge, right? So then you flip a sign, and so then that's a place where students are going to go, they're going to wander off, going, okay, well, why is the sign, and do I understand that? And so you want to anticipate those places where you might need to give students a little bit more time to process it. I think your interaction with the class is, twofold. One is that you didn't ask us too many questions. You didn't ask us to do much. So maybe you could work on that a little bit. But in terms of your eye contact, and you're moving around and you're looking, I feel like you were talking like to me. And hopefully other people felt that as well. That, you know, you really made great eye contact and great connection. So that was great for sure. All right, great.
So next time I will try to reduce the number of slides and the content. But one thing is, one have to